We previously looked at the 4 quantum numbers that describe an electron within an atom. And so what we'll do now is we will continue to examine those 4 quantum numbers, provide a comparison with the previous idea of electrons, which was orbits. So we're going to look at orbitals. And then we're going to look at how those quantum numbers all play out in terms of an energy level diagram within an atom. So, with the advent of the wave mechanical model of the atom, and we call it wave mechanics because the electrons we see as behaving like waves. So with the advent of the wave mechanical model of the atom, the quantum numbers began to take on new meanings. Before we continue, let's compare orbits as Bohr described them to orbitals as we now know they exist. So Bohr thought of electrons orbiting in these 2D paths or 3D shells around the nucleus. But orbitals, however, we now know are effectively 3D spaces of electron probability. Bohr also thought that electrons traveled as particles along a fixed path or fixed distance around the nucleus. However, we now know that it is impossible to know both the location and momentum of an electron. So we do not talk about fixed paths anymore. What we talk about are basically these orbitals, which are effectively enclosed spaces that contain high probability. And when I say high probability, I say high probability of finding an electron within that enclosed space. Bohr previously thought that orbits had circular or even elliptical shapes. However, orbitals have really no distinct shape. In fact, the shape depends on the quantum number. So what I'll write is no distinct shape. Because the shape depends on the quantum number. Bohr also defined that an electron, or rather an energy level, can fit 2n squared electrons per energy level, right? This calculation still works out today, that if you have the principal quantum number, you can calculate the number of electrons per energy level, right? Or per orbit. But we know that an orbit contains sublevels, or these subshells called orbitals, and each subshell can only contain 2 electrons. So an orbital can only contain 2 electrons. Let's take a look at what we mean by this. Well, we'll go back up to our previous note here. And we'll take a look at this diagram on the right. As we can see, this is 1s. 1 is your designation for your principal quantum numbers. So that means in this case right here, we are only at the first energy level. And we know at the first energy level, we only have 1 orbital, and that's the s orbital. And this orbital can only fit 2 electrons. Okay. In the second energy level, we have 2 possible orbitals. If you can refer to our notes right here, in the second energy level, we have 2 possible orbitals. We have s orbital and p orbital. Remember that there are 3 orientations of the p orbital. So we have the s orbital here that can fit 2 electrons, but then the pz orbital can fit 2 electrons, the py orbital can fit 2 electrons, and the px orbital can fit 2 electrons. So altogether, this makes 8 electrons. When we take a look at n equal to 3, n equal to 3 means we have an s orbital, we have the p orbitals, and we also have the d orbitals, each of which contain 2 electrons. So when n is equal to 3, we have an s orbital containing 2 electrons. These p orbitals, each containing 2 electrons, and then these d orbitals, each of those containing 2 electrons. So when n is equal to 3, if we do the math here, we actually can find out that there are 18 possible electrons on the 3rd energy level. So Bohr's calculation still holds true today. 2n squared is equal to the number of electrons per principal quantum number. Going back to the table that we have here, the quantum numbers now have specific meanings in terms of electron clouds and shapes. The principal quantum number n is the main energy level of the electron. The secondary quantum number, L, is the subshell, and that basically gives you the shape of the orbital. Okay, and remember that means that L represents either S, P, D, F, in fact. We haven't gotten to F yet, but that's the next one. Magnetic quantum number is M sub L, and that's its orientation in 3D space. So for example, the P has 3 possible M sub L numbers because there's the orientation along the x-axis, there's the orientation along the y-axis, and there's the orientation along the z-axis. And then there's an electron spin, which remember recall it is either positive 1/2 or negative 1/2. And so that's either your up spin or your down spin, or clockwise or counterclockwise spin. Again here, this is more review. When L is equal to 0, the subshell symbol is S. And remember, S is just the one spherical orbital, and so there's only one of them, right? And that can contain 2 electrons, that one spherical s orbital. When L is equal to 1, that represents the p orbital, and there are 3 orbitals, as we can see here. They're along the x, y, and z axis. When L is equal to 2, that's the d orbital, and we saw previously that there are 5 types of d orbitals. Finally, when L is equal to 3, we end up with the f orbitals, and there are 7. And we can see that as we increase by 1 in the value of L, the number of orbitals goes up by 2. There is also a discrepancy in the energy of each of these orbitals. So S has the lowest energy of these types of orbitals. Then P has more energy, then D has more energy, and then F has more energy after that. Okay, so we'll say right here, the s orbitals, they have the lowest type of energy, and then F has the higher type of energy. And in fact, it doesn't just go past F. It increases to G, so on and so forth. But we're only really going to concern ourselves, in fact, mostly with S, P, and D, but also somewhat with F as well. Okay, it says right here, do you feel confused? Well, it probably does seem a little confusing because this is all new material, and this is not how we have previously described the electrons within atoms in our curriculum. But hopefully an energy level diagram will help with your understanding of how electrons fit within an atom. So this is an energy level diagram. When completing an energy level diagram for an element, the lower energy orbitals must be filled first. That makes sense. When we previously did our Bohr-Rutherford diagrams, we started on the first energy level and then we filled up the next energy levels sequentially. Remember that each orbital, or each circle here, can hold 2 electrons, one with a positive spin, up spin, and one with a negative spin, down spin. So here's the procedure. You count the number of electrons in an atom equal to the number of protons. You fill the low energy space with an electron, and before moving up to the next energy sublevel, you add an additional electron of opposite spin. If you have multiple orbitals in the same energy level, spread the electrons out as much as possible before doubling up, and you write the basic electron configuration below. Okay, so here we go. We're going to take a look at this. Remember, this right here is the first energy level, and it only has an s orbital. Okay, so that's going to get 2 electrons. This right here is the second energy level. And remember, the second energy level has both s and p. And so we fill these up before going on to the third energy level. The third energy level, we have an S and a P. We also have D within the third energy level. But this is the tricky part, okay? Because before we can fill up 3D, we actually have to fill up 4S first. And you might think, well, why are we going to the fourth energy level before we're done filling up the third energy level? Well, this has to do with the principle we learned on the previous page. Take a look. This is 4s and this is 3d. D orbitals typically have more energy than s. So even though this d orbital is in a lower main energy level, it still has slightly more energy than the 4s because the 4s has lower energy. So the order would be 1s, 2s, 2p, 3s, 3p, 4s, back to 3d, then 4p, then 5s, then again back to 4d, 5p, 5s, 4f, 5d, and 6p. So it does get a bit complex because of the energies of the sub-levels versus the main principal quantum numbers. All right? Okay, so let's do an example first. Okay, we'll start with oxygen. So the first part of doing these energy level diagrams is to figure out how many electrons does oxygen have when it is electrically neutral. Well, oxygen should have 8 electrons when it is neutral because it has 8 protons, so therefore it has 8 electrons. So we're going to start off at the beginning here with the 1s orbital. Okay, and we have to fill that up first before moving to higher energy levels. So we fill this up with 1 electron in the positive spin, and then before we can move on, we have to double up. And so we now have placed 2 electrons within the first energy level. I have to show a big jump because there is a big jump of energy between the first principal quantum number and the second principal quantum number. So then I write 2s, I do another line, that's my 2s orbital. It can fit 2 electrons, so I go 1, 2. I've now placed 4 electrons, and I still have to place another 4. So I need to go up to the next level. Well, that's right there, 2p. 2p. Okay, so I'm going to go, before I double up, I have to go 1, 2, 3. They spread out as much as possible, and then they will double up, right? It's kind of like students getting on a bus. Students getting on a bus, everybody will grab a window seat first with nobody beside them, and then when there are no empty seats left, people will start doubling up, right? So we placed 1, 2, 3, and now I have 1 left to place. I'll double up here, and so these are what we call unpaired electrons. These are my paired electrons, these are my unpaired electrons, and now I have actually done the energy level diagram for oxygen. And I can go ahead and I can actually now write the electron configuration, which is as follows. 1s with 2 electrons, 2. 2s, 2 electrons in that orbital, okay, 2. Then 2p, and in the 2p, remember I have 3 orbitals, 1 along the x, 1 along the y, 1 along the z, and I have 4 electrons there. And this is what we call the electron configuration for oxygen, because it shows the electrons existing in the different energy levels and in the different subshells or the orbitals. Let's now move on to magnesium. Magnesium has 12 electrons. And so with 12 electrons, we start with the first energy level, and I'll try and do this a little smaller because I'm going to need a bit more space here. And so I put in my two electrons in the first energy level. Okay, there we go. So I've got 2 electrons, 10 left to place. I show a big jump. And you absolutely do have to show a big jump because you are communicating to the person reading your work that you understand there is a significant energy jump from the first energy level to the second energy level. 2s is like this, and we put another 2. 2p, you can see it right there, right, is another 3. And we do have to indent them somewhat. And we're going to, so this is 2, 4, 5, 6, 7, 8, 9, 10. All right, so what do we do next after 2p? Well, we go to 3s. So we do 3s right here, and we put in the last 2. And so now we have 12 electrons. So I will now write 1s2, 2s2, 2p6, 3s2, and that is my electron configuration for magnesium. All right, now we're going to get to bromine, and bromine is far more complex because it's going to involve going back and forth between 2 different principal quantum numbers. Let's see what I mean by that. Bromine has 35 electrons. So we're going to have to use quite a lot of space here. So I'm going to go right down to the bottom here, and I'm going to write 1s, and I'm going to try and do it pretty small, and I'm going to put my 2 electrons there. Then I'm going to do a jump between 1s and 2s, and I'm going to make it relatively large, but not very large because I need the space. 2s right there, 2 electrons, 2p. So I've only placed 4, so I can keep going because I have, 35 to put. Sorry. I knew this was going to fill up, so I just doubled them up right away. And then 3s right here, double that up. 3p. Okay. So just recall, this is really what you should be doing. Go across first and then double up. Okay, so I have 2, 4, 6, 8, 10, 12, 14, 16, 18. Well, I'm still not close to my 35, so I've got to keep going. After 3p, recall, you might think to yourself, well, the third energy level has a d orbital, so shouldn't I go to the d orbital? No. Remember that the 4s has lower energy than the 3d, so we have to fill up the 4s first before we can move to the 3d. So after 3p, I'll go to 4s, I will fill that up, and then I will go back to 3d, and I will indent that even further. And remember that the d orbital, or the d subshell, has 5 different orientations in 3D space, each of them containing 2 electrons. And so what I'll do here, I'm just going to zoom out a little bit here. What I'll do here is I will go 1, 2, 3, 4, 5, and then I'll double up. And after I'm done with the 3D, I have to go back to the 4p. Okay, so let's count how many electrons we've placed so far. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, which means that I have 5 electrons left to place. So 1, 2, 3, 4, 5, and I'm left with an unpaired electron. And that actually makes sense because remember that the halogens, which bromine has, usually just have that one unpaired electron needed for bonding. So if I was to write my electron configuration for bromine, I'm going to write it as follows: 1s2, 2s2, 2p6. So remember, these subscripts represent how many electrons are within that sublevel. Then 3s2, 3p6, 4s2, 3d10, and then I'll have to go over here, 4p5. Okay, zoom out a bit so you can see what I've done here. Okay, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then 4p5 right there. 3 principles you must abide by. Pauli's exclusion principle. No two electrons can have the same set of quantum numbers. So that means that each electron within the atom has its own unique set of quantum numbers. So for example, this electron, one of these electrons here, has n is equal to 1, L is equal to 0, M sub L is equal to 0, and if we looked at this one right here, M sub S is equal to -1/2. So what you can never have in an atom is, for example, 2 electrons that are both spinning in the same direction. That is not allowed. Okay, that's a violation of Pauli's exclusion principle. The Aufbau Principle. Electrons must be added to the atom starting with the lowest available energy level and subshell. So that means when we add electrons to atom, we start with low energy, then we go to higher energy, and so on and so forth. The Aufbau principle is what we have to follow when we go to 4s instead of going directly to 3d, because 4s has less energy than 3d does. And Hund's rule. Electrons must be spread out within a subshell with the same spin before doubling up in the orbitals. That just means as follows, right? If you had 3 electrons to place within a p orbital, you have to place them as follows: 1, 2, 3. If you were to do it this way, 3 electrons and you did this, that would be incorrect. That's a violation of Hund's rule. This Aufbau diagram here can also be drawn out to help you figure out the order in which to fill the orbitals. So you write 1s, 2s, 3s, 4s, so on and so forth, and then you just go along here and the arrows show you the orbitals that you need to fill. So you start with 1s, then 2s, then 2p, 3s, then 3p, 4s, then 3d, 4p, 5s, so on and so forth. So this is just kind of a helpful diagram to help guide you through filling energy level diagrams. All right, so this concludes energy level diagrams and quantum numbers and atomic orbitals. Thanks for watching.